Welcome to Chapter 4 of AP Biology, where we're going to talk about what makes the carbon atom so special versus all the other atoms and elements that there are, as well as a little bit about the organic chemistry. Just the basics, but just as to why that's so important. We've talked about water and why that was kind of critical for life, so we're going to talk about what makes it so special that we discuss organic chemistry so much when we talk about life as well. So organic chemistry itself is going to be based around carbon. And this was critical because when we were first looking at life itself, trying to figure it out, a lot of people initially thought that life was something that kind of was put upon you by something else. This was the idea of vitalism, where there was this idea that something else acted upon you and turned you into something alive. And that was essentially replaced by mechanism, where we started to understand the laws that rule chemistry, that rule, basically physics, and how those applied to allowing life to function without needing something else. That a living cell can make a living cell, and it doesn't need somebody else to kind of act upon it for that to work. And so as they studied a lot of this chemistry and they got these natural laws, they also stumbled upon a particularly special atom that makes up many, if not most, of the molecules within living organisms that aren't water. And that is ultimately carbon-based compounds. And so we kind of group those together into what is known as organic chemistry. Now, organic chemistry revolves around carbon because carbon's a special guy. Carbon has 4 valence electrons. That's why they call it tetravalent. So if you see that, that's all it's referring to. And because it's tetravalent, it wants to form 4 covalent bonds. And these 4 bonds that it forms is about the max that you can do as an element. So it's very, very good at connecting with other things, which give it lots of possibilities. If you can only form 1 bond, you don't have as many options. If you can form bonds with 4 separate things, you get a lot more options. Now, the other cool thing it does is it likes to bond with itself. And so it's willing to form these large carbon compounds, such as graphite and diamond, because a lot of elements either don't like themselves, they don't really want to bind together with other elements like them, or they'll bind together, but only like 2 of them. So you have like hydrogen gas will be like H2. That's it. It's not that impressive. If you look at oxygen, you'll see O2, and occasionally you'll get ozone, O3. But that's about it. You don't see things like we see with carbon, where it's carbon in the thousands, the millions, the billions, and well beyond that to some of these, seemingly unimaginably large numbers, because it likes to bind to itself. So that's kind of another cool thing about not just having lots of bonds, but being willing to bond to itself. And then lastly, because it likes to form so many bonds, it can not just form single bonds, which if you're somebody like hydrogen, that's pretty much all you do is single bonds. It can't just form single and double bonds, which would fit with something like oxygen. It can also form triple bonds. So this allows for it to have kind of all the bonding options that there are. If you're a covalent compound, carbon can manage that. So that's one of the things that makes it unique, is its willingness to bond in just about every imaginable way that an element can. Now, with carbon, this is just, we talked about it binding to itself. We call those structures that consist of carbon bonded to itself allotropes. So this just shows you some of the different versions that you have where it can form sheets, where it forms like these elaborate structures called buckyballs that look like a soccer ball, where you can get the carbon tubes. And so these just give us a lot of the options that are just carbon. That's it. We're not looking at throwing in the mix here, because if I add hydrogen, I get a different compound than just carbon. If I add in chlorine, carbon and chlorine will make a different compound with different physical characteristics than just carbon. Same thing if I add both hydrogen and chlorine. That'll be different than if it was just hydrogen or just chlorine. So that start to get this idea of the mind-boggling amount of compounds that we can make, because if I just switch one little guy, like put a hydrogen on this carbon, that's different than if I were to just put one hydrogen on this carbon. And so with these big structures that consist of, trillions of carbon atoms, the ability to kind of just swap out small numbers of other things that are mixed in there gives us brand new molecules with, in many cases, brand new characteristics. So organic chemistry is a huge chemistry field. Life in general, when it uses these organic chemicals, has an insane number of options to choose from, which is what helps allow it to have so many characteristics. Now, having talked about how carbon can have all these different kind of partners, I will say that with organic chemistry, the number one partner that you're going to see is going to be hydrogen. So if I talk about organic chemistry, the first thing that should pop in your mind is hydrocarbons, carbon and hydrogen. Because in many structures, like this is basically lipids, and these long chains are just carbon and hydrogen. So each of these kind of points here is a carbon. They just draw them as points to simplify it. And each of these has the rest of its bonds that it needs with hydrogens. So carbon wants 4 bonds. Right here you can see it just has 2. So what actually is going on here is there's going to be these hydrogens attached to it, these 2 extras, to fill it out, so that carbon has 4 bonds. That gives it essentially what seems to be an octet, which makes it energetically content. And so this is what you're going to see as kind of like the default when we talk about organic chemistry. Now there will be other guys that are mixed in. Oxygen you'll see is a very common one. That's probably the third most common. And you can see that at the head region, the top part of this fatty acid, that there will be this region that does actually have oxygens attached. You know, many other things like carbohydrates have lots of oxygens. So by all means, if we're going to mix in a third guy there, it's normally going to be oxygen. But by default, organic, think carbon, hydrogen. These are important because these carbon-hydrogen bonds are first of all nonpolar, which is why you'll see here that we've got a layer of oil on top, which is essentially just hydrocarbons. And on the bottom here we have water, and they're not mixing because remember, water is polar, oil is nonpolar, and those two guys don't like each other. Polar things don't really like nonpolar things. They can't attract them. You know, polar things want to be around other polar things. You know, they're attracted to them because the difference or the opposite in charge. Same with ionic materials. But neither ionic materials nor polar materials are going to have that attraction to nonpolar things. Now, nonpolar things can be attracted to each other just in the sense that it keeps them away from polar things. Just like if it's cold around you, you might huddle together with other people to avoid the cold that you don't really, want to hang out with. So because these guys chemically want to avoid the polar things, they kind of repulse each other, you will see that the oil will stick together on the top. The other really cool thing about hydrocarbons is these bonds that they have are high energy bonds. So when we break and reform them, we give off a lot of energy. And so this is why so many things like fats that we eat provide us with more energy than proteins or carbohydrates. This is why we can take hydrocarbons like coal and natural gas and oil, and we can extract tons of energy from them to allow us to do tremendous feats of work, moving huge objects long distances with relatively small amounts of actual fuel. And that comes down to hydrocarbons. And you can see here some biologically stored hydrocarbons with this cat, which is storing a rather large amount of fat within its body from having likely been overfed a whole bunch. And that fat would be very useful if you were to starve the cat because it could rely on that for energy. Now obviously if you just have a ton of it, it does add weight to the organism. And so that can also be a hindrance though if you have too much, because I doubt this cat at this weight is going to be a very prolific hunter or be very agile. This cat's probably just going to sit around and wonder if it can have cheeseburger. Now with carbon compounds, we said there's lots of different ways that you can kind of arrange them because the carbons are willing to bind to other carbons, they're willing to bind to other elements in general, and so it's kind of cool that with a lot of these organic chemicals you can get isomers, which means they have the same chemical formula. So if I were to write this out, I might say that glucose, for instance, is C6H12O6, and so is fructose. So they're isomers because they have the same general elements in the same numbers, but they're just arranged differently. Kind of like you might have a room that has a coffee table, a couch, and a lazy boy, and you can arrange them differently in that room even though it's still the same pieces. You don't have to line them up the same way. And there's 3 basic types of isomers. Now the simplest one I'll start with is structural. A structural isomer means that I've completely changed the way that it's arranged. So you'll see right here that we have these 3 carbons, is what we have here. And what I've done is in this one, there's a straight line of them, and then I've got an OH at the end. A structural isomer would just take that OH group and move it to a completely different spot. In this case, it's in the middle. I can also embed the oxygen in the middle of the chain. Each of these is completely restructured. I'm not doing just some minor change where I twisted something. I literally kind of like dismantled a chunk and then reattached it in a completely different way. That's a structural isomer. A structural isomer you can look at, and it's very obvious initially that it is not the same thing when you look at its actual structure. Now, geometric isomers are a little bit more interesting. So for this isomer, you can go through and you can see that there's these R guys, and I don't care what they are. We can just think of them as being R for right now, but they could be chlorine atoms, they could be OHs, whatever. So let's kind of ignore the numbers for now just to make it simpler. So we've got R's and H's. If I go through and have a structure where I put the R's where they're both kind of facing up, if you will, that's one arrangement. And you'll notice this double bond here. So if I go through and I just rotate that double bond 180 degrees. So I started out with both my R groups up, but I rotate that bond 180 degrees. Now one of the R's is pointing up and one is pointing down. This molecule will not behave exactly the same as the molecule where they're both facing up. So that's a geometric isomer where usually there's a double bond and you typically just take wherever that double bond is and you just rotate it. So you still form it, you just form it where the guy that was down before is now facing up. And you can see this one pretty clearly, just you have to look and say, all right, are they both at the top or is one at the top, one at the bottom? And that's what we see with geometric isomers. Now the most difficult one to kind of understand for some people is enantiomers. Now enantiomers are what we call mirror images. So the idea here is if you look at my hands, you can see that they pretty much are the same layout. We've got a thumb, we've got 4 fingers, and if I kind of face them to each other, if this was a mirror, you would see what looks to be that as the mirror image, right? The thumb would be on the same side pointing towards me. My little fingers are pointing towards the camera in this case. So these look like mirror images. But if I go through and then flip them, you can obviously see they're not identical. I can't just say, oh yeah, I could cut off my left arm, my left hand, and I could just reattach to my right and it wouldn't be a big deal. There is a big deal because if I go ahead and line them up now, you'll see the front of my hand is facing forward when my thumb is out, and for this hand it's the back of my hand when the thumb is in the same direction. So enantiomers seem like they're just this minor difference, but you can ask the people who made thalidomide if that's a big deal, because thalidomide was a drug, an antidepressant. When pregnant women took it, one of the enantiomers caused terrible birth defects. And so there are cases where the other version of this enantiomer can have different properties and cause major complications, major issues, even though it's something as seemingly simple and innocuous as being a mirror image. Now, the last thing that we're going to discuss, and I just want to touch on this lightly, is what's called functional groups. I want to make sure I highlight that I'm not going to make you memorize these. So don't go through going hydroxyl, carbonyl, carboxyl, aminos. I don't need you to do that. But what I do want you to realize is as we change out, so let's say we've got this compound that originally was some carbons, and it has some hydrogens. If I were to go through and remove some of these hydrogens and swap it out for an oxygen, in this case we could have a double bonded oxygen, I could have an OH, whatever. If I swap it out for something other than a hydrogen, it ultimately gives that compound certain characteristics that are different than if it just had a hydrogen. So if I had something like this hydroxyl group, an OH, that typically makes you more polar. So it will make you behave differently than if you were just carbon and hydrogen. And so it's important a lot of times to understand that minor changes, for instance, like the carboxyl group is kind of interesting because this tends to make things acidic. So if I add a carboxyl group instead of just a hydrogen, I'm ultimately going to get something that would be an organic acid. It's likely to be at a pH that's less than 7. If I add amino groups, it's kind of cool because this tends to make things basic. So what you add to these things, just these tiny changes in what's attached to your carbons, can affect your overall end product, and in many cases it can do so in a fairly predictable way. And so I want you to appreciate that organic chemistry is a huge field. And this is one of the reasons that life has so many options that we can get so many of the cool things, the enzymes, DNA, so many of these neat molecules that we use for so many different purposes. Being catalytic to help us do chemical reactions, storing information. We've got stuff storing energy. All that stuff is largely possible because of the breadth of the molecules that we can form due to things like functional groups, due to things like these single, double, triple bonds, due to the fact that carbon can bond to itself. It allows for life to have a tremendous diversity and a tremendous adaptability.